I'm so glad you found your way here. Right now, you're traveling through space at over 1 million miles per hour, carried along by our galaxy as it drifts through the darkness. Tonight, you'll discover how the Milky Way moves through the universe in ways we're only beginning to understand. And by the end, you'll see that stillness is only an illusion. Everything, including you, is always on a journey. Welcome to 100 Sleepy Facts. Wherever you are right now, perhaps looking up through your window at the stars, or simply resting beneath the turning sky, allow yourself to feel the gentle motion of our cosmic home. We'll drift through 100 space facts about galactic movement, from our sun's quiet orbit around the galaxy's heart to the way entire galaxies dance through empty space, to the mysterious forces pulling us toward distant shores we'll never reach in our lifetimes. These quiet journeys through space create a cosmic community of peaceful minds. Feel free to like and subscribe or share a thought down in the comments. It helps others find their way here, too. One sleepy soul at a time. It means the universe to us. Settle deeper into your pillows now. Let your shoulders drop. Your breathing slow and steady. You don't need to hold on to any of this cosmic knowledge. Just feel that peaceful heaviness spreading through you, like you're floating weightless in the vast, silent darkness between stars, drifting gently toward sleep. Close your eyes and breathe deeply. You're floating where starlight paints pathways through infinite space. Let your mind drift with cosmic silence. And now we begin. The Milky Way is moving through space at approximately 1.3 million miles per hour. This remarkable speed, roughly 600 kilometers per second, is measured relative to the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This ancient radiation provides astronomers with the closest thing we have to a universal reference frame, a cosmic ruler against which to measure true motion through the universe. From this perspective, our entire galaxy is streaming through space like a leaf carried on an invisible river. The direction of this motion points roughly toward the constellations Leo and Virgo, toward a region of space where massive concentrations of matter create gravitational pulls across millions of light years. Yet, despite this tremendous speed, you feel nothing. No wind, no acceleration, just the stillness of your bed beneath you. Our Sun orbits the center of the Milky Way at about 514,000 miles per hour. Recent measurements using data from the Gaia spacecraft have refined this figure to approximately 230 kilometers per second, give or take a few kilometers. This means that with each breath you take, our Sun travels roughly 1,400 miles along its orbital path around the galaxy's heart. The Sun is located about 26,000 light-years from the galactic center, positioned in what astronomers call the Orion Spur, a minor spiral arm between two larger arms. At this speed, it takes our Sun approximately 230 million years to complete one full orbit around the galaxy, a period astronomers sometimes call a galactic year or cosmic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 trips around the galaxy, each one a journey of nearly 150,000 light-years. The Milky Way doesn't rotate like a solid disk. Instead, different parts move at different speeds, a phenomenon called differential rotation. In our solar system, Planets farther from the Sun move more slowly, following Kepler's laws. Neptune crawls along its orbit while Mercury races around, but galaxies work differently. Stars in the outer regions of the Milky Way move at roughly the same speed as stars closer to the center, creating what astronomers call a flat rotation curve. Between 200 and 220 kilometers per second is the typical stellar orbital speed for most of the galaxy. This unexpected pattern puzzled astronomers for decades because visible matter alone couldn't explain it. The stars should slow down the farther out you go, but they don't. This observation became one of the first strong pieces of evidence for dark matter, an invisible substance that seems to make up most of the galaxy's mass, holding the outer stars in their surprisingly swift orbits. We experience multiple motions simultaneously: Earth's rotation, Earth's orbit, the Sun's galactic circuit, the galaxy's cosmic drift, all happening at once. Einstein taught us that constant, smooth motion is indistinguishable from rest. Only changes in speed or direction can be detected. Since all these cosmic motions carry us steadily forward, we perceive them as complete stillness, the peaceful quiet of a universe flowing smoothly through space and time. Only acceleration, a change in velocity, reveals itself through forces we can feel. But these cosmic motions are smooth and steady, carrying you along like a passenger in a perfect vehicle, creating the experience of complete rest. The Andromeda galaxy is moving toward us at approximately 68 miles per second. That's about 110 kilometers per second, or roughly 250,000 miles per hour. For over a century, astronomers have known that Andromeda's light is blue-shifted, meaning its wavelengths are compressed by motion toward us rather than stretched by motion away. This makes Andromeda one of the few galaxies in the visible universe approaching the Milky Way, while nearly all others are receding due to cosmic expansion. Andromeda and the Milky Way are the two largest members of our local group, a collection of more than 100 galaxies bound together by gravity within a region about 10 million light-years across. These two giants dominate the group, their mutual gravitational attraction drawing them together across the 2.5 million light-years that currently separate them, like two dancers slowly moving toward embrace. They approach each other through the darkness. Research published in Nature Astronomy in 2025, led by Till Sawala at the University of Helsinki, suggests the certainty of a Milky Way-Andromeda collision is not as definite as once thought. For years, astronomers predicted an inevitable merger in about 4 to 5 billion years, when our two galaxies would collide and eventually merge into a single giant elliptical galaxy, sometimes called Milkomeda. But new calculations using data from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft paint a more uncertain picture. When researchers account for the gravitational influences of other local group members, particularly the Triangulum Galaxy and the Large Magellanic Cloud, the probability of collision drops significantly. The study found only about a 50% chance of merger within the next 10 billion years. The massive Large Magellanic Cloud, orbiting perpendicular to the Milky Way-Andromeda path, may disrupt the expected trajectory enough to turn a direct collision into a near miss, leaving both galaxies to continue their separate cosmic journeys. The Milky Way and Andromeda are separated by about 2.5 million light-years, and that distance is shrinking, Every second, the gap between these two massive spiral galaxies closes by 68 miles. Every hour, they draw 244,800 miles closer. Every day, nearly 6 million miles of ancient darkness disappears between them. Yet, despite this constant approach, they remain unimaginably far apart. Light leaving Andromeda tonight won't reach Earth for 2.5 million years. If a message could somehow travel between the galaxies at light speed, a simple hello, and how are you exchange would take 5 million years to complete. On human timescales, the distance is essentially eternal, as vast now as it will be in all the centuries humans might endure. But on cosmic timescales, the separation is temporary, a brief interval in the long story of galactic evolution, a pause before the possible embrace. Our local group of galaxies is itself moving. The entire collection, the Milky Way, Andromeda, Triangulum, and all the dwarf galaxies bound to them, travels as a unit through space at approximately 390 miles per second, relative to the cosmic microwave background. That's about 630 kilometers per second, or roughly 1.4 million miles per hour. This motion carries us toward the Virgo cluster, a massive collection of galaxies about 65 million light-years away that contains roughly 1,500 galaxies, including giants much larger than the Milky Way. The Virgo cluster itself is moving, pulled by even larger structures. It's like a river within a river, currents within currents, all flowing together through the cosmic ocean. Every scale of structure, from planets to solar systems to galaxies to clusters to superclusters, moves in relation to others, creating a hierarchy of motion that extends across billions of light-years. The Great Attractor is pulling the Milky Way and thousands of other galaxies toward it. Located roughly 150 million light-years away in the direction of the Hydra and Centaurus constellations. The Great Attractor is a gravitational anomaly so massive that it influences the motion of galaxies across hundreds of millions of light-years. It's not a single object, but rather a massive concentration of matter, including galaxy clusters and dark matter, that creates an overwhelming gravitational pull. The Milky Way's motion through space at 1.3 million miles per hour is partly a response to this enormous gravitational influence. But the Great Attractor itself is being pulled by something even larger. Beyond it lies the Shapley supercluster, an even more massive collection of galaxies whose gravity influences an even larger region of space. It's a cascade of attraction, each structure pulled by something bigger, motion within motion, all the way to the largest scales of cosmic structure. The cosmic microwave background reveals our motion through the universe. This faint radiation, a relic from 380,000 years after the Big Bang, fills all of space with nearly uniform temperature of 2.7 Kelvin, just barely above absolute zero. But the uniformity isn't perfect. When astronomers mapped the cosmic microwave background in exquisite detail, they noticed that in one direction of the sky, the radiation appears slightly warmer, while in the opposite direction it appears slightly cooler. This temperature difference, tiny but measurable, creates what's called a dipole pattern. It's caused by the Doppler effect, the same phenomenon that changes the pitch of a passing siren. As the Milky Way moves through space, we're moving toward some regions of the microwave background and away from others. The radiation from regions we're approaching appears blue-shifted to higher frequencies and thus warmer, while radiation from regions we're leaving appears red-shifted and cooler. This dipole pattern is how astronomers determined our true velocity through space, our motion relative to the universe as a whole. It's the closest we have to measuring our absolute speed, our movement through the cosmic reference frame itself. Measurements from 2009 found stars at the galaxy's edge moving at 158 miles per second, far faster than visible matter alone could explain. This observation, repeated across thousands of galaxies, provided compelling evidence that an invisible substance, now called dark matter, makes up most of the galaxy's mass, holding fast, moving outer stars in their orbits through gravity we cannot see but can measure. Based on the distribution of visible matter, stars, gas, dust, these outer stars should be moving much more slowly, perhaps 60 miles per second or less, but they're not. They move almost as fast as stars much closer to the center, despite being much farther from the galaxy's central mass. This flat rotation curve, where orbital velocity stays roughly constant with distance, was one of the first convincing pieces of evidence that galaxies contain far more matter than we can see. Without dark matter, those fast-moving outer stars would fly off into intergalactic space, unbound from the galaxy's gravity. Recent studies from 2024 suggest that stars at the galaxy's outer edge may be moving more slowly than expected. Researchers at MIT measured velocities around 173 kilometers per second at distances of 27 kiloparsecs, notably slower than the 230 kilometers per second near the Sun. However, some astronomers suggest this apparent slowdown might result from using simplified disk models rather than more accurate spherical models for the outer halo. The debate continues, reminding us that even measuring our own galaxy's rotation remains challenging. This unexpected dip, if confirmed, suggests that the galaxy's gravitational core may be lighter in mass than previous estimates, possibly containing less dark matter than once believed. The discovery challenges long-held assumptions and reminds us that even our own galaxy, our home for billions of years, still holds surprises in its distant reaches. In the cold darkness, where scattered stars circle slowly through the dark matter halo. The Milky Way is not moving alone through empty space. It's embedded in a vast cosmic web of dark matter, gas, and galaxies that stretches across the observable universe. This cosmic web formed in the first billion years after the Big Bang, as tiny variations in matter density grew under their own gravity, creating filaments and sheets of material separated by vast voids. Galaxies form where these filaments intersect, where matter concentrates into nodes dense enough to ignite star formation. The Milky Way sits on one such filament, moving along streams of matter that connect it to other structures. Recent research suggests that the local group of galaxies, including the Milky Way and Andromeda, lies on a dark matter filament that has guided the growth and motion of local galaxies over billions of years. The motion we measure isn't random wandering. It's movement along invisible highways of gravitational influence, channels carved by dark matter, paths that connect our galaxy to the larger architecture of the universe. The Sun's motion isn't perfectly circular. As it orbits the galactic center, the Sun also bobs up and down through the galactic plane. like a horse on a carousel that moves both around and up and down. Our solar system crosses through the midplane of the Milky Way's disk approximately every 33 million years, oscillating above and below by up to 230 light-years from the central plane. Right now, the Sun is positioned slightly above the galactic midplane and moving upward, rising through the disk's northern side at about 7 kilometers per second. In roughly 14 million years, we'll reach the maximum height of this oscillation, then begin falling back through the plane toward the southern side. This bobbing motion is caused by the gravitational pull of matter in the galactic disk. The combined mass of billions of stars and vast clouds of gas that create a gravitational sheet pulling everything toward the midplane. Like a weight on a spring, we oscillate through equilibrium, never quite settling, always in gentle motion above and below the plane. The Milky Way's motion through the local group is complex. While Andromeda approaches at 110 kilometers per second, other local group members move in different directions with different speeds. The Large Magellanic Cloud, our nearest major galactic neighbor, orbits the Milky Way at a distance of about 163,000 light-years and approaches us at roughly 50 kilometers per second. The Small Magellanic Cloud, slightly farther away, moves at a different velocity along a different path. The Triangulum Galaxy, third largest in the local group at 2.7 million light-years away, may be gravitationally bound to Andromeda, or may be on its own independent trajectory. Dozens of dwarf galaxies scatter through the local group, each with its own velocity relative to the Milky Way, some approaching, some receding, some passing by. It's a complex dance of gravitational attraction and momentum, each member influencing the others, all bound together by gravity, yet each moving along its own path through space. The local group is not static. It's dynamic, evolving. Its members constantly rearranging their relationships as they move through time. Gravity travels at the speed of light. This fact, predicted by Einstein's general relativity and confirmed by observations, has profound implications for galactic motion. When a galaxy moves, the changes in its gravitational field propagate outward at light speed, not instantaneously. For nearby structures like Andromeda, just 2.5 million light-years away. This means we're responding to where Andromeda was 2.5 million years ago, not where it is now. The gravitational pull we feel from the Great Attractor, 150 million light-years distant, reflects its configuration 150 million years in the past. On cosmic scales, we're all responding to each other's ancient positions, pulled by gravity's ghost images of where massive structures used to be. Yet, because these motions are generally smooth and change slowly compared to light-to-travel time, this doesn't significantly affect our trajectories. The universe's choreography, though delayed by light speed, maintains its rhythm. Each galaxy moves through space responding to gravity's messages from the past. But those messages change slowly enough that the dance continues unbroken. The Milky Way is gaining mass. Every day, our galaxy accretes material from its surroundings, slowly growing larger as it sweeps up gas, dust, and even entire dwarf galaxies. The Large and Small Magellanic Clouds, our two largest satellite galaxies, are gradually being absorbed, their gas being stripped away by the Milky Way's gravitational pull to form the Magellanic Stream. a vast arc of hydrogen gas stretching more than 200,000 light-years across the southern sky. The Sagittarius Dwarf Elliptical Galaxy is currently colliding with the Milky Way, its stars and dark matter mixing into our galaxy's disk. Over billions of years, many small dwarf galaxies have likely been consumed entirely, their stars now indistinguishable from those born within the Milky Way itself. This process of galactic cannibalism, though slow and gentle compared to major mergers, gradually increases the Milky Way's mass and alters its structure. The galaxy we inhabit is not the same galaxy that formed 13 billion years ago. It's been growing, feeding, changing shape, always in motion, always evolving. High-velocity clouds race through the Milky Way's halo. These clumps of hydrogen gas, some containing millions of solar masses, move at speeds often exceeding 300 kilometers per second relative to the galaxy's rotation. One of the most famous is the Smith Cloud, a gas cloud currently plunging toward the Milky Way's disk at 150 miles per second. It contains enough hydrogen to form about 1 million stars and will crash into the galactic disk in approximately 30 million years, triggering a burst of star formation in the collision zone. Where these clouds come from remains somewhat mysterious. Some may be material ejected from the Milky Way by past supernovae or stellar winds, now falling back. Others may be pristine gas from intergalactic space, never before incorporated into stars, falling into the galaxy for the first time. A few may be remnants of dwarf galaxies torn apart by tidal forces, their gas scattered but still recognizable as distinct clouds. Whatever their origins, they represent matter in motion, gas streams flowing through the galaxy's gravitational field, fuel for future generations of stars, all moving to gravity's ancient pull. The Milky Way's spiral arms are not permanent structures. Recent computer simulations suggest that spiral arms may be density waves, regions where stars and gas temporarily concentrate as they orbit through the galaxy, rather than permanent features rotating with fixed stars. Imagine cars on a highway slowing down through a construction zone. The traffic jam moves along the road at a different speed than the individual cars, which enter the jam, slow down, then speed up again as they exit. Similarly, stars enter spiral arms, slow down slightly due to increased gravitational density, then exit on the other side, while the arm itself persists as a pattern moving through the disk at a different angular velocity than the stars. This means the spiral arms we see are not composed of the same stars over time. Stars drift in and out of the arms as they orbit. The beautiful spiral pattern is transient, a wave pattern in the stellar density field, not a rigid structure. The Milky Way's appearance is always changing, its spiral arms constantly reforming and dissolving, matter flowing through patterns that seem stable but are actually fluid, like eddies in a stream. The galactic center holds a supermassive black hole, named Sagittarius A star. This monster contains about 4 million times the mass of our Sun, all compressed into a region smaller than Mercury's orbit. The black hole doesn't significantly affect the Sun's motion, as we're too far away for its gravity to dominate. But objects closer to the center orbit the black hole at tremendous speeds. Some stars near Sagittarius A star complete orbits in just 16 years, racing around the black hole at up to 3% of light speed. The center itself moves in response to its surroundings, wobbling slightly as gas and stars orbit it, creating a proper motion across the sky that astronomers can measure with precise observations. By combining measurements of the Sun's orbital speed with observations of Sagittarius A star's motion, astronomers have refined their estimate of the distance to the galactic center, now known to be about 26,000 light-years, give or take a few hundred. The heart of our galaxy, though invisible from Earth behind vast clouds of dust, pulses with motion, a dark anchor around which everything else revolves. The Milky Way's disk is warped. Rather than being perfectly flat like an ideal disk, the galaxy's outer regions bend and twist, creating a shape more like a warped vinyl record than a flat plate. This warp becomes more pronounced farther from the center, with the disk deviating up to several thousand light-years from true flatness at the outermost edges. The cause of this warp is still debated, but it likely results from gravitational interactions with satellite galaxies, particularly the Large and Small Magellanic Clouds, whose gravitational tugs distort the outer disk as they orbit around the Milky Way. The warp rotates, precessing around the galaxy like a wobbling top, completing one full precession cycle every few hundred million years. Recently, astronomers using data from the Gaia spacecraft detected a wobbling motion in the disk that might be caused by torques from this warp, or from matter accreted from satellite galaxies, or from the misalignment between the disk's rotation axis and the dark matter halo's principal axis. The Milky Way, it turns out, is not a perfect, pristine spiral. It's a messy, warped, wobbling structure shaped by billions of years of gravitational interactions, a galaxy that bears the scars of its history in its very shape. Escape velocity at the Sun's location is approximately 330 miles per second, or about 528 kilometers per second. That's how fast an object would need to move to escape the Milky Way's gravitational pull entirely and drift into intergalactic space. This high escape velocity reflects the combined gravitational pull of all the galaxy's matter, both visible stars and gas, and the invisible dark matter that dominates the total mass. A few stars in the Milky Way do exceed this escape velocity, having been accelerated by supernovae explosions or ejected from binary systems by complex dynamical interactions. These hypervelocity stars are doomed to eventually leave the galaxy, traveling alone through the vast intergalactic void. For the Sun and most other stars, however, orbital speeds remain well below escape velocity. We're bound to the Milky Way, held by gravity, destined to orbit the galactic center for billions of years to come, never straying too far from home. The Milky Way's total mass is still uncertain. Different measurement methods give values ranging from 0.7 trillion to 2 trillion times the mass of the Sun, a spread that reflects the genuine difficulty of weighing the galaxy from the inside. Most of this mass is dark matter, which doesn't emit light and can only be detected through its gravitational effects. Some estimates come from measuring the orbital velocities of satellite galaxies and using those speeds to infer how much mass must be present to keep them bound. Others use the rotation curve of stars within the disk, or the vertical motion of stars bobbing through the galactic plane, or the escape velocity measurements. Each method has its own uncertainties and assumptions. Recent research combining multiple techniques suggests a mass around 1.5 trillion solar masses within 200,000 light-years of the center. But the uncertainty remains large, perhaps a factor of 2 in either direction. We don't yet know precisely how massive our own galaxy is. We're like insects trying to weigh the Earth by measuring tiny gravitational tugs, feeling the effects of mass we cannot directly see. The Andromeda galaxy may be more massive than the Milky Way, or they may be roughly equal, and astronomers aren't entirely sure which is true. Early estimates suggested Andromeda was perhaps twice as massive, containing about 1 trillion stars compared to the Milky Way's 200 to 400 billion. But more recent measurements of both galaxies' dark matter halos suggest they may be closer in total mass than previously thought. Both around 1.5 trillion solar masses, with uncertainties large enough that their true masses might be reversed. What we do know is that Andromeda appears larger and brighter in the sky, not just because it's intrinsically bigger, but also because we're viewing it from outside, seeing its full extent. While we observe the Milky Way from within its disk, our view obscured by dust. The two galaxies are remarkably similar in many ways, both large spiral galaxies with multiple spiral arms, both attended by dozens of smaller satellite galaxies, both roughly 100,000 light-years in diameter, both containing central supermassive black holes, both moving through space at similar speeds. They are cosmic twins, separated by distance but alike in nearly every measurable way. The speeds involved, hundreds of kilometers per second, millions of miles per hour, reveal forces beyond human experience. Energies so vast and smooth that they feel like perfect stillness. We move through space at velocities that would cross the entire planet in seconds. Yet we feel nothing. Safe in gravity's embrace. Free to rest, to sleep, to dream, while the cosmos carries us gently through the dark. The question of how the Milky Way moves through space connects to deeper questions about our place in the universe. For millennia, humans believed Earth stood still at the universe's center, with everything else revolving around us. Then we learned Earth orbits the Sun. Then that the Sun orbits the galactic center. Then that the galaxy moves through space. Each discovery displaced us further from cosmic centrality. We learned we're not at the center of anything, just passengers on a planet orbiting a typical star in an ordinary galaxy, moving through the universe like countless others. Yet this displacement brings its own kind of wonder. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the telescopes we aim at the heavens, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that ancient astronomers breathed while watching these same stars move across the sky. We are all space travelers, flying on a small planet through the galaxy. Now we continue. The Virgo supercluster contains our local group along with thousands of other galaxies. This enormous structure spans roughly 110 million light-years and contains at least 100 galaxy groups and clusters, including the massive Virgo cluster that gives the supercluster its name. The Milky Way sits on the outskirts of this structure, far from the dense center where thousands of galaxies crowd together. Recent surveys suggest the Virgo supercluster contains roughly 47,000 galaxies, though many are too faint to observe directly. The entire supercluster is bound by gravity, with all members moving in complex patterns influenced by the collective gravitational pull of all that mass. Our local group moves toward the Virgo cluster at speeds between 100 and 400 kilometers per second, falling slowly inward over hundreds of millions of years. But the Virgo supercluster itself may be part of an even larger structure called the Laniakea supercluster, which contains perhaps 100,000 galaxies stretched across 520 million light-years. Whether these vast structures are truly gravitationally bound or merely transient groupings that will dissolve as cosmic expansion continues remains an open question. The universe itself is expanding, causing distant galaxies to move away from us. This expansion, discovered by Edwin Hubble in the 1920s, means that space itself is stretching, carrying galaxies apart like dots on an inflating balloon. The farther away a galaxy is, the faster it recedes. A galaxy 1 billion light-years away recedes at about 50,000 miles per hour. A galaxy 2 billion light-years away recedes at 100,000 miles per hour. This relationship, called Hubble's law, reveals that the universe was once much smaller and denser than it is today, leading to the Big Bang theory of cosmic origin. But on smaller scales, where galaxies are close enough for gravity to overcome expansion, this pattern breaks down. Within the local group, Andromeda approaches us rather than receding. Gravity here is strong enough to pull galaxies together despite cosmic expansion. It's only on scales larger than a few hundred million light-years that expansion dominates, carrying structures apart faster than gravity can pull them back together. The universe expands, but locally, gravity creates islands of approach and collision. The cosmic microwave background allows us to measure something close to absolute motion. In most of physics, there's no such thing as absolute rest or absolute motion, only relative motion between objects. Einstein's relativity teaches that all inertial reference frames are equally valid, and you can only measure your motion relative to something else. But the cosmic microwave background provides a special reference frame, the rest frame of the universe as a whole, defined by the nearly uniform radiation field filling all of space. Observers who see the cosmic microwave background as perfectly uniform in all directions, with no dipole pattern, are at rest in this cosmic reference frame. The Milky Way is not at rest. We see a strong dipole pattern, with the microwave background appearing warmer in the direction of our motion and cooler behind us. This reveals that the galaxy moves at 600 kilometers per second relative to the cosmic average. It's as close as we can come to measuring our absolute velocity through space itself. The Large Magellanic Cloud may significantly affect the Milky Way Andromeda encounter. This satellite galaxy, visible to the naked eye from the southern hemisphere as a fuzzy cloud, contains roughly 20 billion stars and orbits the Milky Way at about 163,000 light-years distance. Recent research suggests the Large Magellanic Cloud is more massive than previously thought, perhaps 10 to 20% of the Milky Way's total mass when dark matter is included. Its gravitational influence is therefore not negligible. Computer simulations from 2025 show that when the Large Magellanic Cloud's gravity is properly accounted for, it affects the Milky Way Andromeda trajectory significantly. The cloud's orbit is nearly perpendicular to the line connecting the Milky Way and Andromeda, creating sideways tugs that can alter the expected collision course. This effect, combined with uncertainties in the galaxy's exact masses and velocities, is part of why recent studies find only a 50% chance of collision rather than the near certainty predicted a decade ago. Small influences from seemingly minor players can have major consequences in cosmic dynamics. In the first few billion years after the Big Bang, when the universe was smaller and denser, galaxies were closer together, and collisions were far more common. Many large galaxies grew primarily through mergers during this early epoch, consuming smaller galaxies to build up mass. The Milky Way experienced several significant mergers in its past, including one about 10 billion years ago, with a galaxy nicknamed Gaia Enceladus that disrupted the early disk. In the modern universe, major mergers have become rare in regions like our local group. Most galaxies now move apart due to cosmic expansion, and only gravitationally bound groups still experience collisions. The Milky Way's era of violent growth has largely ended. We're in a quieter time, slowly accreting small satellites, but unlikely to face another major merger for billions of years, if ever. The Sun's velocity through the local standard of rest is about 13 kilometers per second. The local standard of rest is a theoretical frame of reference that represents the average motion of stars in the Sun's neighborhood, as if they moved in perfectly circular orbits around the galactic center. But the Sun doesn't move in a perfect circle. It has a peculiar velocity, a small deviation from the average motion, that carries it slightly faster than some neighbors and slightly slower than others. This peculiar velocity has three components: motion toward the galactic center, motion perpendicular to the plane, and motion in the direction of galactic rotation. The Sun is currently moving inward toward the center at about 7 kilometers per second, upward through the disk at about 7 kilometers per second, and ahead of the average rotation by about 10 kilometers per second. These small deviations from perfectly circular motion result from gravitational perturbations, slight tugs from nearby stars and giant molecular clouds that nudge orbits over millions of years. The solar system's path is not perfectly smooth. It's slightly bumpy, gently wobbling as it circles the galaxy. Dark energy is causing the universe's expansion to accelerate. Discovered through observations of distant supernovae in the late 1990s, this unexpected finding revealed that not only is the universe expanding, but that expansion is speeding up, not slowing down as gravity would suggest. Some unknown form of energy, dubbed dark energy, seems to fill all of space with a repulsive effect that pushes matter apart at large scales. This acceleration means that distant galaxy clusters are receding from us faster now than they were billions of years ago, and will recede even faster in the future. Eventually, billions of years from now, only the galaxies in our local group will remain visible. All others will have receded beyond the cosmic horizon, their light so redshifted that it becomes undetectable. The local group will become an island universe, alone in an expanding darkness, with no visible evidence that other galaxies exist beyond our small collection. But this fate lies so far in the future that it remains almost abstract, a prediction for a universe transformed beyond recognition, long after the Sun has died. The Triangulum Galaxy's role in the local group remains uncertain, located about 2.7 million light-years away, roughly the same distance as Andromeda, but in a slightly different direction. Triangulum is the third largest member of our galactic neighborhood. It contains perhaps 40 billion stars, making it about 40% the mass of the Milky Way, but still substantial by galactic standards. Astronomers aren't entirely sure whether Triangulum orbits Andromeda as a satellite or moves independently through the local group. The two galaxies are separated by only about 750,000 light-years and appear to have experienced a close passage 2 to 4 billion years ago, which triggered waves of star formation across Andromeda's disk. Computer simulations of the Milky Way-Andromeda encounter show that including Triangulum increases the merger probability, as its gravity can nudge the two larger galaxies toward collision rather than a near miss. Triangulum itself may eventually merge with the Andromeda Milky Way system if a collision occurs, though probably not during the first encounter. The local group's future depends on the complex gravitational interplay between these three spiral galaxies and dozens of smaller companions. Hypervelocity stars have been ejected from the Milky Way at speeds exceeding escape velocity. These rare objects, moving faster than 500 kilometers per second, are doomed to leave the galaxy and wander alone through intergalactic space. Most hypervelocity stars originated near the galactic center, where close encounters with the central black hole can accelerate stars to tremendous speeds through a process called the Hills mechanism. When a binary star system passes too close to Sagittarius, a star, tidal forces can tear the pair apart, with one star falling into the black hole while the other is flung away at breakneck speed. A few hundred hypervelocity stars have been identified so far, though the actual population may be larger. These wandering stars drift alone through space, their paths gently revealing the invisible dark matter landscape through which they travel. Some were ejected millions of years ago and have already reached the Milky Way's outer halo, still racing outward toward their lonely futures beyond the galaxy's edge, never to return. The Milky Way's rotation is affected by the distribution of dark matter. Cosmological simulations suggest that dark matter forms a roughly spherical halo surrounding the visible galaxy, extending far beyond the disk of stars and gas. This halo may stretch out several 100,000 light-years, perhaps even farther, containing most of the galaxy's total mass. The exact shape and density profile of the dark matter halo affects how stars orbit. If dark matter is more concentrated toward the center, rotation curves will rise steeply, then flatten quickly. If it's more evenly distributed, rotation curves will rise gradually and stay flat to larger distances. Recent observations suggesting a declining rotation curve at the Milky Way's outer edge have sparked debate about whether dark matter is less abundant in the outer halo than previously thought, or whether observational challenges are affecting the measurements. Some astronomers argue that if we use spherical models rather than disk models to analyze the data, the apparent decline disappears and the rotation curve remains flat. The shape of the rotation curve directly constrains dark matter's distribution, making these observations crucial for understanding the galaxy's invisible scaffold. Proper motion measurements reveal the motion of stars across the sky, while radial velocity tells us how fast a star moves toward or away from us. Proper motion measures sideways motion, the star's apparent movement across the celestial sphere over time. For distant objects like other galaxies, proper motion is extremely small and difficult to measure. requiring decades of observations with the most precise instruments. The Hubble Space Telescope and the Gaia spacecraft have revolutionized proper motion measurements, achieving precision better than a millionth of a degree per year. These measurements allowed astronomers to determine that Andromeda's tangential velocity, its sideways motion perpendicular to our line of sight, is much smaller than its radial approach velocity. This finding confirmed that Andromeda is indeed on a collision course with the Milky Way, moving almost directly toward us rather than passing by at an angle. Proper motion studies have also revealed streams of stars with unusual velocities, remnants of destroyed dwarf galaxies, and allowed precise measurements of the Sun's motion around the galactic center. Watching stars drift slowly across the sky over years and decades reveals motions that span millions of light years. The Milky Way's magnetic field affects how gas moves through the galaxy. This field, though incredibly weak by everyday standards, about 1/millionth the strength of Earth's magnetic field, extends throughout the galactic disk and halo. Charged particles in gas clouds feel the magnetic force, causing them to spiral along field lines as they orbit the galaxy. The magnetic field is thought to play a role in star formation, regulating how quickly gas clouds can collapse, and in launching galactic winds that carry gas out of the disk. Recent observations using radio polarization and the alignment of cosmic dust grains have begun mapping the Milky Way's magnetic field structure in detail. Initial results from 2024 suggest the field has a complex topology, with regions where field lines twist into spirals and other regions where they remain more ordered. Understanding the magnetic field helps explain why some gas remains stable in the disk for millions of years, while other clouds rapidly collapse to form stars. The galaxy's invisible magnetic threads guide the flow of matter just as surely as gravity, channels through which cosmic weather flows. Galaxy collisions trigger bursts of star formation. When two galaxies pass through each other, their gravitational fields compress gas clouds, increasing their density beyond the threshold needed for collapse. This compression can trigger a starburst, a period of rapid star formation that converts huge fractions of available gas into new stars over just a few 100 million years. Examples of ongoing galaxy collisions in the nearby universe show dramatic increases in star formation rates. The Antennae galaxies, two spirals currently merging about 45 million light-years away, contain regions where stars are forming hundreds of times faster than in the Milky Way's disk. If the Milky Way and Andromeda do eventually collide, a similar starburst may occur, though probably less intense than in some observed mergers because both galaxies will have consumed most of their gas by then, billions of years in the future. Still, the collision would likely create enough compression to ignite millions of new stars, briefly lighting up the merged system before the gas is exhausted, leaving a giant elliptical galaxy dominated by old red stars. The velocity dispersion of stars reveals the galaxy's gravitational potential. Velocity dispersion measures how spread out stellar velocities are in a particular region, how much individual stars' velocities differ from the average. Near the galactic center, where the gravitational field is strong and complex, stars have high-velocity dispersions, ranging randomly in different directions with speeds of 100 to 120 kilometers per second. Farther out in the disk, where motion is more ordered and orbits more circular, velocity dispersion drops to 20 to 40 kilometers per second, The vertical velocity dispersion, how fast stars bob up and down through the disk, is even smaller, typically 10 to 20 kilometers per second. These numbers reveal how much kinetic energy stars possess, and thus how deep the gravitational potential well is at each location. Higher dispersion means deeper potential, stronger gravity, more mass. By measuring velocity dispersions throughout the galaxy, astronomers map the gravitational field and thus constrain the total mass distribution, including dark matter. The random motions of stars, their disordered wanderings, trace out the shape of the invisible gravitational landscape through which they move. Our understanding of galactic motion has evolved dramatically over the past century. 100 years ago, astronomers barely recognized that galaxies existed as separate objects beyond the Milky Way. The Great Debate of 1920 centered on whether spiral nebulae were small gas clouds within our galaxy or enormous island universes far beyond it. Edwin Hubble settled the question in the mid-1920s by identifying Cepheid variable stars in Andromeda, proving it lay millions of light-years away, far beyond the Milky Way's edge. The same observations revealed Andromeda's blue shift, its approach toward us. By the 1970s, Vera Rubin's rotation curve measurements provided strong evidence for dark matter. In the 1980s, the Great Attractor was discovered. In the 2000s, dark energy was confirmed. And now, in 2025, new data from Gaia and Hubble are revising our predictions about the Milky Way-Andromeda collision. Each generation of astronomers refines our understanding, revealing new complexities in motions we thought we understood. The universe's choreography, though governed by simple laws of gravity and motion, plays out in ways that continue surprising us, always deeper, always more subtle than previous theories suggested. You're still here, still awake, still drifting with us through these stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I and everyone listening in the quiet dark, floating through facts like stars drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. The Sun will eventually be flung to a different region of the galaxy if a collision occurs. Computer simulations of the Milky Way-Andromeda merger show that most stars survive unharmed, as the vast distances between stars make direct collisions astronomically improbable. But gravitational forces during the encounter will dramatically rearrange stellar orbits. Stars currently in the disk may be scattered into elongated orbits that carry them far from the galactic plane. The Sun, currently orbiting about 26,000 light-years from the center, might end up much closer to or much farther from the central region. Some simulations show the Sun being ejected entirely into the merged galaxy's halo, orbiting hundreds of thousands of light-years from the new center. Even if the Earth still exists at that time, billions of years hence, the night sky would look completely different, with the galactic disk far away and only the stars of the halo nearby, scattered sparsely through the darkness. Gravitational waves from galaxy collisions are too low in frequency for current detectors. When galaxies merge, their central black holes eventually spiral together and collide, releasing tremendous bursts of gravitational radiation. but the frequency of these waves depends on the orbital period of the black holes just before merger. For supermassive black holes like those at galaxy centers, the orbital periods are years or decades, producing gravitational waves with frequencies of nanohertz, billions of times lower than the Hertz range frequencies that LIGO detects. To observe these ultra-low frequency waves, astronomers use pulsar timing arrays, networks of millisecond pulsars whose regular pulses act like cosmic clocks. Tiny shifts in pulse arrival times, caused by gravitational waves stretching space, can reveal merging black holes throughout the universe. In 2023, several pulsar timing arrays announced evidence for a background hum of nanohertz gravitational waves, possibly from countless distant galaxy mergers occurring across cosmic time. The universe rings with gravitational radiation from colliding galaxies, a bass note too deep to hear but detectable through pulsar timing. The Milky Way's collision with the Sagittarius dwarf elliptical galaxy is already underway. This small satellite galaxy, discovered only in 1994 despite being relatively close, is currently passing through the Milky Way's disk, its stars mixing with ours. Tidal forces from the Milky Way's gravity are tearing the Sagittarius dwarf apart, stretching it into long streams of stars that wrap around the galaxy multiple times. Simulations suggest this collision has happened several times already, with the Sagittarius dwarf passing through the Milky Way's disk every few 100 million years. Each passage strips away more stars and gas. Eventually, probably within the next billion years, the Sagittarius dwarf will be completely disrupted, its stars fully absorbed into the Milky Way's halo and disk, indistinguishable from native stars. We're witnessing galactic cannibalism in progress, a slow-motion collision that has been ongoing for billions of years and will continue until one galaxy ceases to exist as a separate structure. The center of mass of the local group lies somewhere between the Milky Way and Andromeda. This point, called the barycenter, is where the combined gravitational pull of all local group members balances out, the point around which everything else orbits. Because Andromeda and the Milky Way are by far the most massive members. The barycenter is determined primarily by their masses and positions. Current estimates place it roughly 450,000 light-years from the Milky Way, slightly closer to Andromeda, suggesting Andromeda may be somewhat more massive. Both galaxies orbit this common center, spiraling toward each other as they circle their mutual gravitational focus. It's not accurate to say Andromeda falls toward the Milky Way or vice versa. Both fall toward their shared center of mass, like binary stars orbiting a point between them. The entire local group is a gravitationally bound system, slowly collapsing as members orbit and merge, eventually destined to form a single massive structure billions of years from now. Time dilation affects motion on cosmic scales, though the effects are usually negligible. According to general relativity, time passes more slowly in stronger gravitational fields and for objects moving at high speeds. The Milky Way's motion at 600 kilometers per second produces a tiny time dilation. With clocks moving with the galaxy running slower than clocks at rest in the cosmic microwave background frame by about 1 part in a million. For stellar mass objects orbiting close to galactic centers, where speeds can reach significant fractions of light speed and gravitational fields are intense, time dilation becomes more significant. A star orbiting close to Sagittarius A star might experience time measurably slower than a star farther out. Over millions of years, these tiny effects accumulate. The universe's age depends on which reference frame you measure from, but for everyday purposes, even on galactic scales, these relativistic effects are small enough to ignore. Newton's laws work fine for understanding galactic dynamics. Einstein's corrections matter primarily near black holes and neutron stars, where gravity and motion reach their extremes. The Milky Way may have formed differently than astronomers once believed. The traditional picture suggested galaxies grew gradually, forming their disks first and then slowly accreting satellite galaxies over billions of years. But recent evidence from Gaia suggests the Milky Way's history was more violent. Many stars in the Milky Way's thick disk and stellar halo appear to have originated in a single massive merger about 10 billion years ago, when a galaxy, perhaps 1/4 the Milky Way's mass, collided with our forming galaxy. This collision, nicknamed Gaia Enceladus after the mythological giant, disrupted the early Milky Way, heating its disk and scattering stars into the halo. The Milky Way we see today is partly built from the wreckage of this ancient collision. Our galaxy's calm appearance, a graceful spiral rotating sedately through space, masks a violent history of mergers and disruptions, a past written in stellar orbits and chemical compositions that reveal their origins in galaxies long since destroyed. Momentum is conserved in galaxy collisions. When two galaxies merge, the total momentum of the system remains constant, even as individual stars' momenta change dramatically. If one galaxy approaches from the left and another from the right, their combined momentum determines how the merger remnant will move. The final velocity is the mass-weighted average of the initial velocities. For the Milky Way Andromeda collision, if it occurs, the merged galaxy will move through space at a velocity somewhere between the two current velocities, depending on the exact mass ratio. Since Andromeda and the Milky Way appear roughly equal in mass and approach each other nearly head-on, the merged remnant will move at a velocity roughly averaging their current motions. The Great Attractor will continue pulling it. The Virgo cluster will continue exerting its gravitational influence. The cosmic expansion will continue carrying distant structures away. The collision changes the internal structure of the galaxies, but doesn't significantly alter the motion of their combined center of mass. The dance continues. Partners merged into one, still moving to the same gravitational music. The Magellanic Stream demonstrates how galaxy collisions strip away gas. This enormous arc of neutral hydrogen gas, stretching more than 200,000 light-years across the southern sky, was torn from the large and small Magellanic Clouds by tidal forces as they orbit the Milky Way. Ram pressure. The resistance gas feels as it moves through the Milky Way's halo, also contributes to stripping. The Magellanic Stream contains enough hydrogen to form hundreds of millions of stars, fuel that's been stolen from the Magellanic Clouds and will eventually fall into the Milky Way's disk. This process of gas stripping is common in galaxy clusters, where rapid motion through hot intracluster gas can remove most or all of a galaxy's star-forming material. The Virgo cluster contains many gas-poor galaxies that have been stripped by their high-speed motion through the cluster's hot atmosphere. Collisions don't just rearrange stars, they redistribute gas, the raw material for future star formation, fundamentally altering galaxies' ability to make new stars for billions of years after the collision ends. Computer simulations of galactic collisions require enormous computational power. To accurately model a galaxy collision, computers must track millions or billions of individual particles representing stars, gas clouds, and dark matter, calculating gravitational forces between them at each time step. A single simulation can take weeks or months to complete even on powerful supercomputers. The earliest simulations in the 1970s and 1980s could track only a few thousand particles, providing rough outlines of how collisions proceed. Modern simulations track billions of particles, resolve fine details of tidal streams and star formation, and include gas physics, magnetic fields, black hole growth, and stellar feedback from supernovae. Despite this progress, simulations still make approximations. Dark matter is easier to simulate than gas, which requires modeling pressure, temperature, and complex chemical processes. The most sophisticated simulations running today combine gravity, hydrodynamics, radiation transport, and stellar evolution, attempting to capture all relevant physics in a single model. Each simulation is a virtual universe, a digital laboratory where astronomers can watch billions of years of galactic evolution unfold in accelerated time. Halfway through our journey, one truth emerges with clarity. The Milky Way's motion through space is not a simple story. It's a layering of movements at different scales, each responding to different gravitational forces. The Sun orbits the galactic center. The galactic center wobbles slightly. The galaxy rotates differentially. The disk warps and precesses. The Milky Way falls toward Andromeda. The local group moves toward Virgo. The Virgo supercluster flows toward the Great Attractor. And beyond that, larger structures pull on superclusters. Motion within motion, orbits within orbits, like a cosmic Russian doll where each scale of structure moves in response to the next larger scale. And all of this happens smoothly, constantly, without friction, without sound, without any sensation of movement. We ride along on Earth, a small planet orbiting a typical star in an ordinary galaxy, yet participating in movements spanning hundreds of millions of light years, carried by forces we cannot feel but can only measure through patient observation and careful thought. Let's pause again and notice where we are in time. Let each breath guide you to realize time is yours, a separate stream that only you are living. While the vast universe continues to spin, expand, change, this second you're breathing, listening, is unique. The Milky Way orbits once every 230 million years, but your heartbeat, your breath, measures a time on a human scale. Cherish the present moment, knowing that right now, your time is unique in the universe, and we continue drifting. Einstein's relativity teaches us that no reference frame is more valid than another. Whether you describe the galaxy as moving through space or space flowing past the galaxy, both descriptions capture truth. The universe operates the same regardless of perspective, governed by laws that transcend any single viewpoint. Motion is relative, definable only by comparison to some chosen reference point. The cosmic microwave background provides a convenient reference, but it's not absolute in any fundamental sense. we could equally well choose a reference frame moving with the Milky Way, in which case the galaxy would be at rest and the cosmic microwave background would be moving. Physics works the same in both frames. The laws governing galactic motion don't depend on which frame we choose. This relativity of motion is humbling. There's no ultimate stillness, no fixed stage on which cosmic drama plays out. Everything moves relative to everything else. Rest is just another word for sharing someone else's motion. Dark matter, halos extend far beyond visible galaxies. While the Milky Way's stars and gas form a disk roughly 100,000 light-years in diameter, the dark matter halo probably extends 5 or 10 times farther, perhaps reaching 500,000 to 1 million light-years from the center. Most of the galaxy's mass resides in this extended halo, invisible but detectable through its gravitational effects on satellite galaxies and stellar streams. The boundary between the Milky Way's dark matter halo and Andromeda's dark matter halo may already be touching or overlapping, even though the visible parts of the galaxies remain 2.5 million light-years apart. In this sense, the collision has perhaps already begun, not in the disks where stars shine brightly, but in the vast dark matter halos that surround them, interpenetrating in slow motion over hundreds of millions of years. By the time the stellar disks approach each other, the dark matter halos will have been interacting for eons, their gravitational fields already merged into a single structure. The local group is relatively isolated. The nearest significant galaxy group is the Sculptor group, about 12 million light-years away, and the nearest large galaxy cluster is the Virgo cluster at 65 million light-years. This isolation means the local group's dynamics are dominated by its own internal gravity, rather than external tidal forces or close encounters with other structures. Many galaxies in denser regions, like galaxy clusters, experience constant harassment from neighbors, frequent near passes that strip gas and distort stellar orbits. The local group is spared this fate. Its members evolve more quietly, shaped primarily by mutual interactions rather than external disruptions. This relative isolation makes the local group an excellent laboratory for studying galaxy evolution in a relatively simple gravitational environment, without the complications introduced by extremely dense surroundings. Yet, even here, motion defines the future, with Andromeda and the Milky Way slowly approaching, the Magellanic Clouds gradually being absorbed, and all the dwarf galaxies slowly falling toward the two massive spirals that dominate the group. The cosmic web's structure influences galactic motion. Galaxies don't move randomly through space. They follow filaments, streams of dark matter and gas that connect galaxy clusters like threads in a web. The Milky Way sits on one such filament, its motion partly determined by the orientation and density of this dark matter highway. Recent research suggests that the alignment of satellite galaxies around the Milky Way and Andromeda may reflect the underlying filament structure, with satellites arriving along preferred directions defined by the cosmic web. These filaments formed in the early universe, arising from tiny quantum fluctuations amplified by cosmic inflation and then grown by gravitational collapse over billions of years. The motion of galaxies today reflects the initial conditions set in the first fraction of a second after the Big Bang. Patterns imprinted when the universe was smaller than an atom, now expressed in structures spanning hundreds of millions of light-years. Velocity measurements require extreme precision. To measure Andromeda's proper motion, the sideways motion across the sky. Astronomers used the Hubble Space Telescope to observe individual stars in Andromeda in 2002 and again in 2010. They compared the positions of these stars against distant background galaxies, which are so far away they appear essentially fixed on the sky. By averaging over thousands of stars, they measured proper motions smaller than 1/10,000,000th of a degree per year, equivalent to measuring the rate of hair growth on someone standing on the moon. This extraordinary precision required Hubble's sharp vision and careful data analysis to separate genuine motion from measurement noise. The result confirmed that Andromeda's tangential velocity is much smaller than its radial velocity, meaning it moves almost directly toward us rather than passing by at an angle. Such measurements push the limits of current technology and reveal nature's secrets only through years of patient observation and painstaking analysis. Galactic orbits are not perfect ellipses. In the solar system, planets follow elliptical orbits to high accuracy because the sun's gravity dominates and planets barely affect each other. But in galaxies, mass is distributed throughout the volume, not concentrated in a central point, and dark matter dominates the gravitational potential. This creates a different orbital behavior. Stellar orbits around galactic centers are rosettes, patterns that precess and shift over time, never quite repeating. The sun's orbit is not a closed ellipse. It's an open curve that, over many circuits around the galaxy, traces out a complex flower petal pattern in space. Gravitational perturbations from spiral arms, giant molecular clouds, and dark matter substructure nudge the orbit slightly, causing the precession. No star follows exactly the same path twice. The galaxy is a dynamical system where perfect periodicity never occurs, where chaos lurks beneath the apparent order, where small perturbations accumulate over time to create motion that, while deterministic, is unpredictable beyond a certain horizon. The Milky Way may be gaining dark matter from its surroundings. As the galaxy moves through the local group, it sweeps through a cosmic dark matter sea, potentially accreting dark matter particles as it goes. This process, though slow, could gradually increase the galaxy's dark matter content over billions of years. Additionally, when the Milky Way absorbs satellite galaxies, it also captures their dark matter halos, adding that invisible mass to its own. Recent simulations suggest the Milky Way's dark matter content has increased significantly since its formation, growing from perhaps 500 billion solar masses to 1.5 trillion solar masses today, as it consumed dozens of smaller galaxies and accreted material from the local group. The galaxy is not just gaining visible mass in the form of stars and gas, it's also gaining invisible mass, dark matter that strengthens its gravitational pull and affects the orbits of everything within it. Unseen but crucial to the galaxy's structure and dynamics. Gravitational slingshots occur during close encounters. When a small object passes close to a massive one, it can gain or lose orbital energy through gravitational interactions, emerging from the encounter with a different velocity than it entered. This process, called a gravitational slingshot or gravity assist, is used routinely by spacecraft to reach distant planets without burning fuel. The Voyager probes gained speed by passing close to Jupiter and Saturn, stealing tiny amounts of those planets' orbital energy. The same process occurs during galaxy collisions. Small satellite galaxies passing close to larger galaxies can be accelerated to higher speeds, sometimes even reaching escape velocity and being ejected from the group. The Large Magellanic Cloud's current high velocity may result partly from gravitational interactions with other local group members, accelerating it beyond a simple circular orbit. Every close encounter redistributes energy and angular momentum, changing velocities, altering orbits, reshaping the dynamical structure of the system. Gravity doesn't just attract, it also accelerates, slows, and redirects, choreographing cosmic motion through pure geometry and mass. The oldest stars in the Milky Way move differently than younger stars. Stars in the thick disk and stellar halo, most of which formed more than 10 billion years ago, have high-velocity dispersions and often orbit in eccentric, tilted paths that take them far from the galactic plane. These kinematics reflect the violent conditions of the early galaxy, when mergers were common and the disk was still forming. In contrast, stars in the thin disk, including the Sun, formed more recently in a calmer environment and orbit the galaxy in nearly circular paths close to the plane. By studying stellar kinematics, the velocities and orbits of different stellar populations, astronomers can reconstruct the Milky Way's history, identifying groups of stars that formed together or arrived together in ancient merger events. Each star's motion carries information about its origin, a fossil record written in velocity and position. The Milky Way is not a single generation of stars sharing a common history. It's a composite, layer upon layer of different populations formed under different conditions, each moving through the galaxy on paths shaped by the forces that created them. The galaxy's motion and history may influence the conditions for life. Star formation rates, which depend on how much gas the galaxy contains and how it moves through space, affect the number of planets that might harbor life. Galaxy collisions trigger starbursts, temporarily increasing star formation and potentially creating millions of new solar systems, each with planets that might someday develop life. Yet, collisions can also disrupt existing planetary systems. The galaxy's motion through space, its interactions with neighbors, all shape the cosmic environment where life emerges. Galactic dynamics and biology connect in unexpected ways. The motion of structures spanning light years, influencing the chemistry of molecules measured in nanometers. The conditions that allowed life to arise on Earth, orbiting a stable star in a quiet region of the galaxy, reflect billions of years of galactic evolution and motion. Gravitational potential energy converts to kinetic energy as galaxies fall together. The Milky Way and Andromeda started separating shortly after the Big Bang, carried apart by cosmic expansion like all matter in the universe. But their mutual gravitational attraction, strong enough to overcome expansion at these close distances, eventually halted the separation and began pulling them back together. As they fall toward each other, gravitational potential energy converts to kinetic energy, increasing their approach velocity. They're like two rocks dropped from opposite sides of a valley, falling toward the lowest point. By the time of closest approach, if a collision occurs, the two galaxies will be moving at several hundred kilometers per second relative to their center of mass. Speeds high enough that they'll pass through each other in tens of millions of years. Not quite fast enough to escape on the first pass. They'll swing around, slow down, and fall back together for a second encounter, then a third, each time losing orbital energy to tidal interactions and dynamical friction, gradually spiraling closer until they finally merge into a single structure. The night sky will look dramatically different during a collision. If Earth somehow survives until the Milky Way Andromeda encounter billions of years from now, residents will witness spectacular changes. Andromeda will loom huge in the sky, thousands of times larger than the Moon, a vast spiral spanning half the sky as the two galaxies approach. During the first passage, the sky will fill with young, bright stars as the collision triggers intense star formation. New star clusters will blaze blue and white. The galactic plane will warp and twist, creating unfamiliar patterns. After the galaxies separate and fall back together, the spiral structures will dissolve, replaced by more chaotic distributions of stars. Eventually, after several passages, the merged remnant will relax into a giant elliptical galaxy, featureless and smooth, with no distinct disk or spiral arms. The sky will contain far fewer distinct features, just a diffuse glow of billions of stars scattered through a giant elliptical structure. All other galaxies beyond the local group will have redshifted beyond visibility, leaving only this single merged galaxy, an island universe alone in an expanding void. Dwarf galaxies in the local group are being tidally disrupted. Many of the small satellite galaxies orbiting the Milky Way and Andromeda are not gravitationally bound structures, but rather dissolving remnants. Streams of stars gradually being absorbed into the larger galaxies. The Sagittarius dwarf has been almost completely torn apart. The Ursa Minor dwarf is being stretched. The Draco dwarf shows signs of tidal distortion. These disruptions occur because tidal forces, the difference in gravitational pull across an extended object, overcome the small satellite's self-gravity. Like ocean tides raised on Earth by the Moon, galactic tides raised by the Milky Way deform satellites, stretching them into elongated shapes. Eventually, the satellite tears completely apart, its stars spreading into a stream that wraps around the host galaxy. This process has been ongoing throughout cosmic time and continues today, visible in streams of stars threading through the Milky Way's halo, ghostly remnants of galaxies that no longer exist as distinct entities. The speed of gravity matters on cosmic scales. General relativity predicts that gravitational waves travel at the speed of light, meaning changes in a gravitational field propagate outward at 300,000 kilometers per second, not instantaneously. For the Milky Way Andromeda system, separated by 2.5 million light-years. This means each galaxy responds to where the other was 2.5 million years ago, not where it is now. The gravitational pull the Milky Way feels from Andromeda points toward Andromeda's position 2.5 million years in the past. But because galactic motions are slow compared to light speed, this time delay doesn't significantly affect trajectories. Over the 2.5 million years, it takes gravity's message to propagate. Andromeda moves only a small fraction of the distance between the galaxies. The effect is similar to aiming at where a slow-moving target will be, rather than where it is now. Important in principle, but small in practice. Only for extremely fast-moving or rapidly changing systems does the finite speed of gravity introduce significant corrections to Newtonian predictions. Cosmic expansion and gravitational collapse are competing forces. On the largest scales, cosmic expansion dominates, carrying galaxy clusters apart at speeds exceeding tens of thousands of kilometers per second. On smaller scales, gravity wins, holding galaxy groups and clusters together despite expansion. The boundary between these regimes, the scale at which expansion and gravity balance, lies somewhere around 10 to 20 megaparsecs, roughly 30 to 65 million light-years. The local group, about 10 million light-years across, is well within the gravity-dominated regime. Structures this size stopped expanding billions of years ago and have been collapsing ever since, their members drawing together under mutual gravitational attraction. The Virgo supercluster, though much larger, is also probably bound, with constituent clusters slowly falling together over hundreds of billions of years. But on scales of hundreds of megaparsecs, expansion dominates, and structures recede forever, never to interact gravitationally. The universe's fate is written in this competition between expansion and gravity, between the cosmic repulsion driving matter apart and the gravitational attraction pulling it together. Stellar encounters during a collision are extremely rare. Though the two galaxies will pass through each other, individual stars are so tiny and so widely spaced that direct collisions between stars are almost impossible. The Milky Way and Andromeda together contain perhaps 600 billion stars, but they're spread across volumes measured in cubic megaparsecs. The average distance between stars in the disk is roughly 5 light-years. During the merger, stars will pass within a few light-years of each other countless times. But actual stellar collisions, where two stars physically touch, will number in the dozens at most, perhaps fewer. To visualize this, imagine two clouds of gnats flying through each other. The gnats pass through the opposite swarm, dodging and weaving, but actual collisions between individual gnats are rare because they're small and the spaces between them are large. Similarly, galaxies are mostly empty space. They can interpenetrate without most of their constituent stars coming anywhere close to touching. The collision is dramatic only on large scales, reshaping the galactic structure while leaving individual stars essentially unaffected. Angular momentum must be conserved during a merger. When two galaxies collide, their total angular momentum, the measure of their combined rotational motion, remains constant. If both galaxies spin in the same direction, the merged remnant will spin relatively quickly. If they spin in opposite directions, the spins partially cancel, and the remnant rotates slowly or not at all. The Milky Way and Andromeda both rotate in similar directions, with their disks roughly aligned, suggesting the merger remnant will retain some spin. But spiral galaxies typically have less angular momentum than their disks suggest, because most mass is in the dark matter halo, which rotates more slowly than the visible disk. During the merger, gravitational interactions transfer angular momentum from the colliding disks outward to the halos and to ejected tidal tails, slowing the central region. The final merged galaxy will probably rotate slowly, if at all. Its angular momentum distributed among billions of stars on eccentric orbits rather than concentrated in an orderly rotating disk. The merger transforms spin into random motion, order into chaos, a spiral's elegant rotation into an elliptical's featureless calm. The Gaia spacecraft has revolutionized our understanding of galactic motion. Launched by the European Space Agency in 2013, Gaia has measured the positions, distances, and velocities of more than 1 billion stars in the Milky Way, with unprecedented precision. This data has revealed the detailed structure of stellar streams from disrupted dwarf galaxies, identified groupings of stars with similar kinematics that indicate common origin, and allowed precise measurements of the Milky Way's rotation curve. Gaia has also measured proper motions of stars in nearby galaxies, including Andromeda, improving estimates of the collision probability. Future data releases, with even more stars and higher precision, will continue refining our understanding of galactic dynamics. Gaia represents a paradigm shift in astronomy, from studying individual objects to analyzing entire populations statistically, from sketching broad outlines to mapping fine details. The spacecraft has given astronomers a view of the Milky Way's structure and motion, revealing our galaxy's complexity in ways impossible just decades ago. Gravitational lensing reveals invisible mass. When light from a distant galaxy passes close to a foreground galaxy or galaxy cluster, the massive object's gravity bends the light, distorting the background galaxy's appearance into arcs or multiple images. The amount of distortion reveals how much mass is present along the line of sight, including dark matter. Gravitational lensing studies of galaxy clusters show that most mass is dark matter, forming extended halos around visible galaxies. For the Milky Way and local group, gravitational lensing is harder to observe because we're inside the system, not viewing it from outside. But lensing of distant quasars by the Milky Way's dark matter halo has been detected, and lensing observations of other galaxy groups provide analogs for understanding the local group's mass distribution. These observations confirm that dark matter dominates the dynamics, providing most of the gravitational pull that drives galactic motion. The concept of a galactic year provides a useful timescale. Just as Earth's orbit defines a year, the Sun's orbit around the galaxy defines a galactic year, approximately 230 million Earth years. The Sun has completed about 20 galactic years since its formation 4.6 billion Earth years ago. Life on Earth emerged about 16 galactic years ago. Dinosaurs lived about 1 galactic year ago. Human civilization has existed for a tiny fraction of a galactic year, less than 1/10,000th of a complete orbit. This timescale helps contextualize cosmic events. The Milky Way Andromeda encounter, if it occurs in 4 to 8 billion years, lies 17 to 35 galactic years in the future. The galaxy's motion and structure change noticeably over a galactic year, with spiral arms moving, tidal streams evolving, and satellite galaxies being slowly absorbed. The galactic year is to cosmic evolution what a human year is to individual development, a natural unit that measures significant change. Chaos theory applies to galaxy collisions. Although the laws governing galactic dynamics are deterministic, meaning the same initial conditions always produce the same outcome, small uncertainties in those initial conditions can lead to dramatically different results. This sensitive dependence on initial conditions is the hallmark of chaotic systems. For the Milky Way Andromeda encounter, uncertainties in the galaxy's exact positions, velocities, and masses mean that predictions about the collision's details are fundamentally limited. Simulations with slightly different parameters produce mergers at different times, with different geometries, with different outcomes for the Sun's final orbit. This chaos doesn't prevent understanding the general behavior. We know that if a collision occurs, it will involve tidal interactions, star formation bursts, and eventual merger into an elliptical galaxy. But the precise details, the exact timing, the specific locations of individual stars remain forever unpredictable beyond a certain precision. Nature allows prediction but preserves mystery, yields general truths but guards specific futures, lets us glimpse what must happen but not exactly how. The Milky Way's motion has been relatively constant for billions of years. The Great Attractor's pull, the Virgo cluster's influence, and the cosmic microwave background dipole pattern suggest our motion has been directed toward roughly the same region of space for most of the galaxy's history. This stability reflects the long timescales of cosmic dynamics. Gravitational forces act slowly on galactic scales, producing smooth, sustained accelerations rather than sudden changes. The galaxy's velocity has gradually increased as we've fallen through billions of years toward the Great Attractor and Shapley supercluster. But the direction has remained fairly constant. This continuity means the night sky's appearance hasn't changed dramatically over cosmic time, at least not from our motion alone. Constellations shift due to the sun's orbit around the galaxy, and nearby stars move across the sky. But the large-scale distribution of visible galaxies has remained roughly constant throughout Earth's history. The universe our ancestors saw, though interpreted differently, was essentially the same universe we see today. Stars in approximately the same positions, galaxies following approximately the same motions, a cosmos that changes slowly enough to seem almost eternal on human timescales. If a collision occurs and awakens the central black hole, the galactic heart might glow softly for a time, brighter than all surrounding stars, then gradually dim again into quietness. When gas falls toward the central black hole during a merger, it forms an accretion disk that heats up through friction, emitting enormous amounts of radiation. This can make the merged galaxy visible across the entire universe, one of the brightest objects in the cosmos. The Milky Way's central black hole, Sagittarius A star, is currently inactive, accreting very little matter and emitting relatively faint radiation. But if the Milky Way Andromeda collision funnels gas toward the central black hole, it might briefly reactivate. This active phase would last a few million years, until the available gas was consumed or expelled, then fade as the black hole returned to quiescence. Active galactic nuclei were common in the early universe when galaxy mergers were frequent, but they're rare today in the nearby universe where mergers are less common. The future of the local group is merger or isolation. If the Milky Way and Andromeda do collide and merge, the resulting galaxy will dominate the local group even more than the current two galaxies do. Smaller members like Triangulum and the dwarf galaxies will eventually be absorbed, creating a single massive elliptical galaxy containing all the local group's mass. If the collision doesn't occur, the Milky Way and Andromeda will pass by each other, perhaps multiple times, with each passage transferring energy and angular momentum until either a merger eventually occurs after billions of additional years, or the galaxies escape each other's influence and separate forever. Meanwhile, cosmic expansion will carry more distant galaxy groups beyond the horizon, making them unobservable even in principle as their light becomes infinitely redshifted. In the far future, trillions of years hence, only the merged local group will remain visible, a single island of light in an otherwise dark and empty universe. the last remnant of the once rich cosmic web, alone as expansion wins its ultimate victory over gravity. The certainty we seek about galactic motion remains elusive, despite decades of observations, powerful telescopes, sophisticated simulations, and theoretical understanding. The Milky Way Andromeda collision's fate remains uncertain, approximately a coin flip according to the latest research. This uncertainty isn't a failure of science, but a reflection of nature's complexity and our limited perspective. We observe from inside one of the galaxies, measuring velocities across millions of light years, inferring masses we cannot see, predicting futures billions of years away. The marvel is not that we have uncertainty, but that we can predict anything at all, that we can peer billions of years into the future and say with any confidence what might happen. The equations are simple. Newton's laws of gravity and motion, but their application to structures containing trillions of times the sun's mass, spanning millions of light years, evolving over billions of years, reveals depths of complexity that humble us. We understand galactic motion, yes, but incompletely, approximately, with a precision that reveals as much about the universe's subtlety as about our knowledge. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Galaxies orbit galaxy clusters. Clusters move through superclusters. The Sun orbits the center of the Milky Way. All are circles. Cycles, endless orbits, like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like galaxies silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. Everything in the universe participates in motion at multiple scales simultaneously. Atoms vibrate within molecules. Planets orbit within solar systems. Stars circle within galaxies. Galaxies drift within clusters. Each scale independent yet connected. Each motion real yet relative, creating a cosmos where change is the only constant. From quantum fluctuations at the smallest scales to cosmic expansion at the largest. Motion pervades existence. To exist is to move. To persist through time is to trace a path through space. Every object has a history written in its trajectory, a future defined by its velocity. The universe is not a static stage on which events occur. It's a dynamic, flowing, ever-changing arena where motion is fundamental and stillness is only ever relative, never absolute. The stars we see are all our galactic neighbors. Every star visible to the naked eye belongs to the Milky Way, most within just a few thousand light years of the Sun. Andromeda appears as a faint smudge, the most distant object easily seen without optical aid. Everything else in the night sky, every constellation, every astronomical object from ancient star charts, all reside within our galaxy. All share its motion through space. We see the Milky Way from inside, our perspective limited by dust and distance. The galaxy's far side remains hidden behind the galactic center. We know the Milky Way's full extent only through observations that penetrate the dust, revealing what optical light cannot. Our view of galactic motion is similarly limited, inferred from velocities we can measure, motions we can extrapolate, all from our single vantage point inside. Over time, As dark energy continues accelerating cosmic expansion, more and more distant galaxies will recede beyond our cosmic horizon. Their light, though traveling toward us, cannot overcome the expansion of space between us. Eventually, within hundreds of billions of years, only galaxies in our local group will remain visible. Everything else fading beyond reach as space stretches faster than light can traverse it. Future astronomers, emerging on planets orbiting stars in the merged local group galaxy, will see an almost empty universe. Just one large elliptical galaxy surrounded by darkness. They won't detect the cosmic microwave background, or see distant galaxies, or observe cosmic expansion. They might conclude the universe is small, static, eternal, unaware of the vast cosmos beyond their horizon, ignorant of the universe's true scale and history. As the galaxy moves at 600 kilometers per second relative to the cosmic microwave background, we experience something analogous to wind on a still day when you're riding a bicycle. The radiation field isn't moving, but our motion through it creates an asymmetry we can measure. Photons from the direction we're moving toward are blue-shifted and higher energy. Photons from behind are red-shifted and lower energy. This pattern affects everything. It means observers in different galaxies, moving at different velocities, experience slightly different radiation environments, see slightly different cosmic patterns. The universe looks different depending on how you're moving through it. Not dramatically different, but measurably so. Enough to reveal your velocity through space. Different generations of stars have different chemical compositions depending on when and where they formed. The oldest stars, formed before many supernovae enriched the galaxy, contain mostly hydrogen and helium. Younger stars, born from gas enriched by stellar nucleosynthesis, contain higher fractions of carbon, oxygen, iron. By measuring stellar compositions and motions, astronomers identify groups of stars that formed together, even if they've scattered across the galaxy. Stars from ancient mergers can still be identified by their distinctive chemistry and orbits. The galaxy's past is written in the motions and compositions of its stars. A history that patient observation can decode, revealing ancient collisions, satellite disruptions, and the gradual assembly of the Milky Way from smaller fragments. The Milky Way's motion at 600 kilometers per second means its total kinetic energy is beyond imagining. Yet we feel none of it. The energy is spread across hundreds of billions of stars, each carrying its share of the galaxy's momentum. For objects moving with the galaxy, this kinetic energy is undetectable, felt only by objects moving differently. Energy and motion are relative, visible only to those moving at different velocities. We carry universe-scale energies, yet experience them as perfect stillness, riding a cosmic wave with power beyond imagination, yet feeling only calm. Spiral arms may be transient features, density waves passing through an ever-changing disk. Stars enter an arm, slow slightly, then exit, accelerating back to typical speed. The arm persists even as stars flow through it, a wave in stellar density moving at a different speed than the stars themselves. This means the spiral pattern is temporary on cosmic timescales, persisting perhaps a billion years before dissipating and reforming. If we could watch the galaxy from outside over billions of years, we'd see the spiral pattern breathe, pulsing with the rhythm of density waves, patterns constantly reforming but never quite the same. As galaxies collide and merge, stars scatter into new orbits, their original trajectories lost. After enough time, the merged system reaches a state where individual stellar orbits are randomized and no memory of initial conditions remains. The final merged galaxy won't show which stars came from which original galaxy. They'll all be mixed together, orbiting in a chaotic tangle with no clear pattern. This erasure of information is entropy increasing, a loss of order that can never be reversed. The universe forgets its past through gravitational relaxation, erasing history as structures merge and mix. Dark matter remains one of the deepest mysteries. We know it exists from its gravitational effects, rotation curves, lensing, cluster dynamics. We know roughly how much exists, about 5 times more than normal matter. But we don't know what it actually is. Hypothetical particles remain undetected despite decades of searching. Alternative theories struggle with observations. The nature of the substance dominating galactic dynamics, the invisible scaffolding shaping cosmic motion, remains unknown. We describe what it does, but not what it is. Map its distribution, but don't understand its composition. Dark matter is the ghost in the machine, the hidden cause of observed effects. The universe holds perhaps 2 trillion galaxies, each drifting like leaves on cosmic currents, each following paths carved billions of years ago, moving together yet separate. Every galaxy has its own velocity, its own trajectory. Some rush toward each other, others drift apart. The universe is a tapestry of motion, individual threads following paths determined by initial conditions set shortly after the Big Bang. The Milky Way is one thread in this cosmic weave, our trajectory shaped by the same forces affecting all others. Everywhere, motion continues. Gravity shapes trajectories. The cosmic dance proceeds according to laws that govern all matter without exception. When we observe Andromeda, we see it as it was 2.5 million years ago, when the light we now detect began its journey. We're looking into the past. If Andromeda changed yesterday, we wouldn't know for 2.5 million years. In a universe where nothing moves faster than light, there is no universal now, no cosmic clock ticking everywhere. Time and space interweave, creating space-time where separation in space implies separation in time. The present of a distant galaxy is forever hidden behind the light travel-time barrier. No observation can pierce. The universe's large-scale structure resembles a vast neural network. Galaxies clustered at intersections, filaments connecting them. This resemblance suggests that certain organizational principles, certain patterns of network formation, emerge naturally in complex systems. The universe organizes itself, creates structure from chaos, builds order from random noise, through gravitational attraction operating over billions of years. And we, conscious beings built from atoms formed in stars. Observe this structure and recognize patterns, finding meaning in motion, beauty in cosmic choreography. Every object's position and velocity uniquely specify its past and future. Given the Milky Way's current state and the gravitational field it experiences, we can integrate equations backward to determine where it was or forward to predict where it will be. Velocity connects past to future, tells us not just where something is, but where it's going. Motion is not separate from existence, but fundamental to it, defining how each object navigates the cosmos. The universe has no center and no edge, only motion relative to other motion. The Big Bang happened everywhere at once, and space itself has been expanding ever since. Every point can consider itself the center. The Milky Way's motion doesn't mean we're moving toward a center or away from an edge. The universe looks roughly the same from every vantage point, with no preferred location. Motion exists, structure exists, but only in relation to other motion and structure, never absolutely. The cosmos is pure relation, pure dynamics, pure change. Most large galaxies experienced multiple mergers during their formation, growing through hierarchical assembly from smaller building blocks. The Milky Way's relatively quiet recent history, with no major mergers in the last 10 billion years, is somewhat unusual. Today's collisions are remnants of a more violent past, rare events in the modern low-density universe. In the early universe, mergers were the primary growth mechanism for massive galaxies, far more common than today. Astronomy is the study of motion observed across time. Every discovery involves measuring how light shifts or positions change. Planets move against stars. Comets trace arcs. Stars drift through constellations. Galaxy positions change over years. Even supposedly fixed objects reveal motion when observed carefully. The universe exists in time as much as space. Astronomy is the study of cosmic motion, of how objects move and change across timescales from seconds to billions of years. We map not static structures, but trajectories. The cosmos is verb, not noun. Process, not object. Eternal becoming. Always in motion toward futures we can glimpse but never fully predict. The Milky Way's motion matters little to life on Earth. The star's light reaches us regardless of velocity. The sun's gravity holds us regardless of how fast we're moving through the cosmos. The physics governing Earth's climate, geology. Biology operates identically whether we're at rest or moving at 1,000,000 miles per hour. Yet knowing about it changes how we see ourselves, recognizing our place in a dynamic, flowing universe. Understanding that we ride along on structures moving through space at speeds we cannot feel. This knowledge enriches existence even without practical application. Science reveals what we cannot feel but can know. Predictions about the far future remain speculative. We can say with reasonable confidence what will happen to the Sun in 5 billion years. We're less confident about the Milky Way Andromeda collision, and we're very uncertain about the universe's fate trillions of years from now. The farther we extrapolate, the more uncertainties multiply. Yet we try, extending current physics as far as possible. Perhaps future civilizations will read our predictions and smile at our mistakes. Or perhaps we've grasped fundamental truths that time will confirm. The attempt to understand cosmic motion across all timescales represents something deeply human, a refusal to be bound by the present. The galaxy is our home and our vehicle. We're passengers on a cosmic ship, sailing through space, carried by forces we barely understand toward destinations we can only guess. The Milky Way protects us, its magnetic field deflecting cosmic rays, its disk providing matter for planet formation. We're embedded in its structure, made from its substance, shaped by its history. The atoms in your body cycled through stars before becoming you, forged in stellar furnaces, ejected by supernovae, mixed in clouds, eventually condensing into the solar system and Earth and life and consciousness. You are made of star stuff, galaxy stuff, material that's been moving through space for billions of years. Perhaps the most remarkable thing is that we can understand it at all. We're tiny creatures on a small planet, living perhaps a few decades, able to observe only a fraction of the universe. Yet, through thought and mathematics and observation, we've deduced that our galaxy moves at 600 kilometers per second, that we orbit the galactic center every 230 million years, that Andromeda approaches, that dark matter dominates dynamics. We have reached billions of years into past and future, mapped structures spanning millions of light years, inferred substances we cannot see, predicted events that won't occur for eons. Human knowledge, imperfect and incomplete, nevertheless grasps real truths, understands motion on scales beyond experience, sees patterns in chaos. This capacity might be consciousness's greatest gift. Nothing is still. Everything moves. From atoms vibrating to galaxies drifting. Motion pervades existence at every scale. To exist in time is to change. To change is to move. Motion may be more fundamental than matter itself, since matter is simply energy arranged in patterns, and energy is the capacity for motion. You are part of this cosmic flow. Your atoms borrowed briefly from space to create the temporary pattern called you, soon to return, recycled into new forms, forever moving. The same forces that move galaxies move planets and atoms. The same dark energy accelerating expansion emerges from quantum scales. The same dark matter shaping galactic rotation affects every photon traveling through space. The same gravity-binding clusters holds your feet to Earth. The universe is unified, all pieces affecting all others, every motion related to every other motion. When you observe the stars, you're seeing light that traveled for years, emitted by objects moving through space. Light red-shifted or blue-shifted by those motions. Every observation is a cosmic story, a chain linking you to distant objects. The Milky Way's journey will continue long after human civilization ends, long after Earth is destroyed, possibly even after the sun dies and becomes a white dwarf fading into darkness. The galaxy moves according to gravity's implacable laws, indifferent to human concerns. Yet for a moment, conscious beings emerged and looked up and understood something of the galaxy's motion. That understanding, however brief, represents something precious. Awareness temporarily coalescing from matter to comprehend the motion carrying it. We are the universe becoming conscious of itself. Stardust contemplating stars. Motion and stillness are both illusions and both realities. You feel still because you share Earth's motion. But relative to distant galaxies, you're moving at tremendous speeds. Both descriptions are equally valid. The universe contains no absolute reference frame. Everything moves relative to everything else. To be is to move. To move is to be. Existence and motion are inseparable. And yet, here in your bed, you can experience perfect stillness, perfect rest, even while knowing you're racing through space. The contradiction is only apparent. Stillness and motion coexist, both real, both true, reconciled in the experience of this present moment. The Milky Way's motion through space is ultimately a question without a final answer. Because motion is always relative. We can measure velocity relative to the cosmic microwave background, or relative to nearby galaxies, or countless other references. Each gives a different answer. Each answer is correct. The question doesn't have one answer, but infinitely many, depending on perspective. And perhaps the deepest truth is this: everything moves together, the entire cosmos flowing forward through time, nothing truly separate, nothing truly still, everything connected. We move not as isolated travelers, but as part of a cosmic whole, our motion inseparable from everything else, one wave in an infinite ocean, one voice in an eternal song. And so, our quiet journey through galactic motion comes to a gentle close. We've traveled from the sun's peaceful orbit around the galaxy's heart to the Milky Way's vast drift through cosmic darkness, discovering along the way that nothing truly stands still, that motion and existence are inseparable, that we ride along on cosmic currents too smooth to feel. From rotation curves revealing invisible dark matter to the uncertain future of our collision with Andromeda, we've glimpsed how the Milky Way is both ancient and changing, both stable and flowing, a galaxy that seems eternal but is actually dancing through space and time, always in motion, always becoming. Galactic motion reminds us that stillness is always an illusion. Much of what defines our cosmic journey happens invisibly, silently, in darkness, guided by gravity we cannot see toward futures we can only imagine. The galaxy teaches patience. Its changes unfold over timescales that dwarf human civilizations. By pausing to notice, we glimpse the extraordinary in what seems ordinary, recognizing that every moment we rest, we're actually racing through space at 1,000,000 miles per hour, carried safely by forces beyond our comprehension. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every star, every galaxy in the universe. You are not separate from the Milky Way's motion. You are a part of it, a temporary pattern of matter and consciousness, riding along on this galactic voyage, sharing the journey with billions of stars. Think about how galaxies drift through space, some approaching, some receding, all following gravity's ancient choreography. Let your entire being dissolve into the gentle darkness, into the soft gravity pulling you into sleep, into the motion that carries all things forward. Prepare for deep sleep. No boundaries left. Only peace. If this gentle journey through the cosmos brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time, but there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. Feel free to let these thoughts of galactic motion fade now, like stars fading at dawn, like ripples smoothing on still water, leaving only peaceful calm behind. Notice how your breathing deepens. Sense the way your body feels heavier, as if Earth's gravity has grown stronger, anchoring you gently to your bed. If sleep comes, simply let it carry you like a galaxy drifting through space, smoothly, inevitably, into a realm where time no longer matters. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the Milky Way will still be there, still circling through space. The stars will still shine. Andromeda will still approach. The cosmos will continue its eternal dance. But tonight belongs to stillness. Tonight belongs to you. Tonight belongs to sleep. Rest well, gentle traveler. And remember, you are made of stardust, moving through space at velocities beyond imagination, yet held safely in gravity's embrace, a small part of something infinitely beautiful. Fall asleep to gentle facts. Dream deeper with bedtime science. Good night.